Okay, so in a question like this, where I'm saying to you, the initial mechanical energy equals the final mechanical energy, I am outright saying no work is being done, because there's no change in energy. How do I know that?
When there's no mention of force changing.
Right, well, there's no mention of force. Okay, that's the first clue. The second clue is there's no mention of work either. Okay, if I don't see the word force or I don't see the word work, okay, it's not a work energy theorem question. Right, it's a conservation of energy question. Another way is in a question that's about conservation of energy, you're going to get both velocities and heights. In a work energy theorem question, you only got one or the other. In a work energy theorem question, work was done and it either changed the kinetic energy of the object, the speed, or it changed the potential energy of the object. It changed the height. But in these questions, you get both. Okay? It's another way that you can tell them apart. Why am I making such a big deal out of this? The most common mistake on the unit exam is people failing to identify what kind of question it is. Okay? I have 100% confidence in your algebra and your math ability to do these questions. I've seen you do that. Okay? I'm not worried about that at all. The trick is always figuring out what math to do. I think I've only said that about 100 times in this unit. Okay? But that's the trick, especially with work energy theorem and law of conservation of energy. So in this question, I have a car drives off a cliff. We're going to say there's no one in it, hopefully. Okay? And it's not like Thelma and Louise. Don't watch that movie. If you've never seen that movie, you have no idea what I'm talking about, don't watch that movie. It's 2 hours of your life you'll never get back. And the best part's when they drive off the cliff at the end. Spoiler alert! Oh wait, I should have said that first. It's terrible. Okay. Speed is, drives off at 25 meters per second. When it strikes the ground below, it's moving at 53 meters per second. Okay? How high is the cliff? All right. When I first read that question, does it look like they're only giving me speeds? Like if I'm just looking at numbers, the only two numbers I see in that question are speeds. Agreed? Is that a way to try to trick you? It is. The other numbers are given to you in the context of the question. You drive off a cliff. Cliffs are generally elevated, sheer kind of drop-offs, okay, that are above some other piece of ground. That would imply that this does have some initial height, because in the end, that's what they're asking me. They're asking me how high is the cliff. Okay? The other thing they tell me is that it strikes the ground. Whenever I see ground level, what's the height? Zero. So they gave me two other pieces of information, but they gave it to me in an underhanded way. Okay? They didn't say the height is 0. They didn't actually write the number out. Okay? They gave me a context that I had to read and get it from there. Okay? This is exactly the kind of thing that tricks people on a test. They don't read the question. They see numbers, they write down the numbers. Okay? And then they're lost because they're like, I don't have enough numbers to do this work energy theorem question. If you don't have enough numbers to do the work energy theorem question, is that a good sign? It's not a work energy theorem question. Probably. Just putting it out there. Okay? Then read the question carefully. Right? This is not a long story. Right? I've given you much longer stories to read to get information from. This is like 3 very short sentences. All right. So I'm going to have you guys try this one, but I'm just going to draw it out as best I can, given my drawing ability. Okay, that's going to be VI, okay, and the height of the cliff is what we're looking for. I'd say that's HI. Okay, and then this will happen all the way to the ground. Okay, here, what did we say the height was? 0. All right, I'm going to give you a little bit of time to see if you can get the math done for that question, and then we'll walk through that. All right, so if we're looking at the solution to this, we've already said it's a conservation of energy question. There's no unconserved or non-conservative forces being mentioned here, friction or anything like that. Okay, so we know that the initial mechanical energy and the final mechanical energy are equal. How much is potential and kinetic is what's changing here. Okay, so we're going to write down the next step, which is always the same. I write down how I calculate the initial mechanical energy and how I calculate the final mechanical energy. Okay, are any of those zero? Which one? Final height is zero, so which energy is zero? Final potential. Okay, guys, am I always doing the steps in the same order? Okay, this is the point where I want to figure out, can I get rid of any of these before I have to do anything else? All right, so what I'm looking for is initial height. That would be part of this term here. All right, I want to get that term isolated before I put in all the M's and B's and H's and G's and all that kind of stuff, because it gets messy after that. Okay, how do I get initial potential by itself?
Subtract the initial.
Right, subtract the initial kinetic over here. All right, so what I'm going to have then is that my initial potential energy equals my final kinetic energy, which happens to be also my total mechanical energy. How do I know that? When it hits the ground, did it have any potential? That means that all of its energy at the end is kinetic. So that EK final also represents my total mechanical energy. If I take my total mechanical energy and subtract the kinetic energy, that should leave me with the potential energy. Agreed? Just a way to kind of work it out logically. If that didn't help at all, forget I said anything. Okay, if you already knew what you were doing with the math. Okay, now I've got this. Am I ready to put in all my formulas? At this point I have to, okay? I have to put HI on the board. I don't have it on the board yet. Okay? So, formula for potential energy, M times G times H initial. Okay? That equals 1/2 MV final squared minus 1/2 MV initial squared. Question never gave me what? Do I need it? I don't. Okay? If the question doesn't give you mass and you don't like that, pick your lucky number. Pick any number. Any number will do. Okay? It's going to cancel out mathematically anyway. You can choose whatever number you want. Okay? I'm going to cancel it because I don't like punching in more numbers than I have to into my calculator. I'm bad at that and I mess up all the time. Okay? So I'm taking the mass out of it. What do I have to do to get HI by itself?
Divide the other side by G.
Right. Divide both sides by G.
Both sides.
Yeah. Okay, and get it over on this side, exactly what you meant, yeah. Okay, so I've got that. Can I put in my numbers? I think I'm ready to put in my numbers. Okay, so I'm going to say then that, let's scroll down a bit here, guys, that initial height is going to equal 9.81, sorry, not 9.81, 1/2. I gotta divide by 9.81 in a minute. 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. All right, everybody okay with that? All right, so I punch that into my calculator. Okay, 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. Okay, I wouldn't want to drive off that cliff, or any cliff for that matter. Doesn't seem like a good idea. Okay, 111.3 meters. All right, questions on how that one worked? Okay, there's a couple of little, like I said, there's a context trick in there. It didn't seem like it gave us any heights, but it did. Okay, we have to kind of be ready for that kind of stuff.
Why do you have to subtract it?
Why am I subtracting this?
Yeah.
Because I brought it over from this side. On this side here, I was adding EK, and I needed to get EP by itself. So the opposite of add is subtract. That's why I brought it over here. Does that make sense? Okay. All right, any other questions? Okay, don't be afraid to ask, guys, if there are. There are no silly questions here at all, okay? Because I'm looking for a height. Height's not squared, right? I have to square if I'm looking for V, because V is always squared. but I don't have to square root this because it isn't squared in the question. That's also a good question. I see people do that a lot. Okay, so no, I don't have to square root if I'm looking for h because h isn't squared in the formula. Okay, anything else? All right. It's a lot of like dangerous behaviors in today's questions. Driving cars off cliffs and jumping out of perfectly good planes. Okay, so in this question here, skydiver jumps out of a plane moving at 90 meters per second and is 10,000 meters above the ground. How fast will the diver be falling when he is 8,000 meters above the ground? Assuming he has not opened his chute, which would of course provide a resistive force of friction. Okay, so during the free fall part of this, what's the only thing acting on him or her? Gravity. Okay? It actually says he in there, so I guess it's a he. All right. Give this one a try, guys. Yeah, give you a few minutes on this one. So if I'm reading through this one here, okay, I've got a skydiver jumps out of a plane. So here's my skydiver. Okay, and we know that when they jump out of that plane, they are at a height of 10,000 meters. And they are moving at 90 meters per second. Now, when you jump out of a plane, the plane is moving horizontally, generally. you don't usually eject out of a plane that's in a steep dive. Okay? Does it matter that that 90 meters per second is horizontal? In the formula for kinetic energy, is it speed or velocity? It's speed. Direction doesn't make any difference. You have kinetic energy if you are moving. Direction is irrelevant. People get confused on this question sometimes because they picture exactly that. When you jump out of a plane, you move at the same speed the plane was moving at. You also begin to move downwards. Okay? But you have kinetic energy because you're moving at 90 meters per second. That is your speed, and as a result, you have kinetic energy regardless of the direction you are traveling. Okay, so if you ever get a question that specifies they're moving, down or up or whatever, that doesn't make any difference. It's speed, it's scalar. Energy is scalar. We never say I have 10 joules of energy to the right. Okay, it's silly, we don't do that. Everyone follow on that? Okay, so that's our initial information. We know that they're going to do this. Actually, they're going to do this. Okay, that's the trajectory that all things that fall out of a plane follow. But okay, we're just going to simplify it and say this. We know that a little while later, they are at a height of 8,000 meters. So that would be their final height. And we are looking for their final speed. Everyone okay with the givens? Okay. As I mentioned, we already said their parachute's not open, so we're going to assume that only gravity is causing them to fall. There's no other forces, no friction or anything like that. Okay, so I can safely say then that the mechanical energy when they first jump out of the plane is the same as the mechanical energy 2,000 meters lower. Okay, so putting in my formulas here for mechanical energy. It's potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Are any of those zero in this situation? They are not. Okay, we initially have potential energy, lots of it, 10,000 meters above the ground. Initially have kinetic energy, lots of it, moving at 90 meters per second. Okay, we have potential energy at the end, still 8,000 meters above the ground, and we still have final, we're looking for final speed. We're obviously going to be moving if we're still 8,000 meters above the ground. Okay, so we can't cancel any of those. What I'm looking for is part of which term? Ava, which term is VF in? Right. So I need to get EKF by itself. All right. So what do I need to move? EPF. How do I move it? I subtract it over to the other side. Okay. So I'm going to subtract EPF. That's going to make it go away. And what I'm going to be left with is my total mechanical energy, okay, all the initial stuff added together, minus my final potential energy. That will leave me with my final kinetic energy. Okay, so I've done that little bit of manipulating. Now I'm gonna put the formulas in and get my final manipulation done. So m times g times h initial plus 1/2 mv initial squared minus mg h final equals 1/2 mv final squared. Is m in every term? Was I ever told the mass of the skydiver? Does the mass of the skydiver even matter? Not in this situation. If I was asked to find the final kinetic energy, it would matter because obviously mass is part of kinetic energy, but because only gravity is acting, the final speed is unrelated to the mass of the object. Okay? If you don't like that, pick any number you like, use your mass if you want to, okay? Doesn't matter, you can plug in any number you want. All right, I choose to enter nothing. So I'm trying to get VF by itself. What do I have to do with the 1/2? Divide it over to the other side. All right, that leaves me with VF squared. What do I want? VF. Sadie, what do I do with this one? Right, this one I square root because I'm looking for VF, which is one of the ones that's squared. Okay, so now I'm ready to punch in all my numbers. So I'm going to have 9.81 times 10,000, okay, my initial height, plus 1/2 times 90 squared, my initial speed, minus 9.81 times 8,000, my final height, divided by 1/2, all under the root. That will get me VF. Okay, so 9.81 times 1,000, times 10,000. I can't believe I'm punching that in when I do it. Okay, plus 0.5 times 90 squared, minus 9.81 times 8,000, divided by 1/2, square rooted. Okay, is that fast? Really fast. Okay, 217.5, actually 217.6 meters per second. Guys, they fell 2 kilometers. They should be going really fast if they fell 2 kilometers. Okay, that's going to make you accelerate in a hurry. All right, so 200. Oh, just got a new one of those. Oh, it didn't break this time. Okay, 217.6 meters per second. Okay, would be the final speed of the skydiver. Everybody okay with that one? All right. Okay, I'm going to give you about a 5-minute break here in the classroom, and then I'm going to put some other ones up, okay, on the board here. Okay, but for now, answer all your pressing snaps and messages and whatever. I give you 5 minutes.
Make a film.
Yes, you can. Okay, guys, let's give this one a try. Oh wait, we just solved for one. We just did one where we were looking for v, didn't we? Okay, let's try this one. So we got a person jumping on a trampoline. Okay, now they're off the trampoline. Trampoline's no longer pushing on them, okay, because they are 1.2 meters above the trampoline, which we'll say is ground level. Okay, so they're not on the trampoline. Trampoline is going to be our ground level. They are 1.2 meters above the trampoline, and they are traveling at 1.5 meters per second. How high can they go? I was recording that whole break too. Okay, so that's the one we're looking at. Okay, how high can they go given this information? There is, I should say, a contextual trick here. Okay, you have to understand what the motion of a person jumping on a trampoline looks like. Okay, I want you to visualize that in your mind. What do they look like when they're as high as they will go? Okay, that might help you to figure out something that may be very important for answering this question. All right, if we're imagining somebody jumping up in the air off of a trampoline, okay, so they move upwards. As they move upwards, what happens to their speed? It decreases. How fast are they going when they're at their maximum height? 0. That's the moment where they turn around and they come back down. That's the context trick to this question, okay, where you visualize what does it look like when something's moving straight up in the air. Well, at some point they have to stop and turn around and come back to earth. Everything, what goes up must come down. That simple rule. Okay, so that's the context trick. Okay, the givens are that our initial height is 1.2 meters. Okay, and our speed initial is 1.5 meters per second. Our final speed is 0. That's the trick. Did I press record? Yeah, okay. And we're looking for our final height. Okay? Oh, that just was all bad. Okay, we're looking for our final height. Is that making sense there? Okay, so no mention of any forces, right? We were very clear about the fact they're no longer on the trampoline, no more work is being done. This is strictly an energy question, conservation of energy question. Okay, so EI equals EF. Okay, we put in our formulas here, EP initial plus EK initial, that's our initial mechanical energy, equals our final mechanical energy, EP final plus EK final. Okay, any simplification I can do here? Is one of these 0? Which one?
Energy kinetic final.
Right, kinetic energy final. Okay, we've already specified that at the highest point in the flight, the upwards, or the velocity of the speed, I keep saying velocity, the speed of the person will be 0 at that point. Okay, now that's eliminated. What I'm looking for is HF, which is part of this term. So, hey, bonus, I don't have to move very much. Okay, that thing's already isolated, so I don't have to do any adding or subtracting. I can go straight to plugging in my formulas. So M times G times H initial plus 1/2 MV initial squared equals M times G times H final. I was never told the mass of the trampoline jumper. Trampolinist? I don't know what you'd call that. Okay, so I'm going to cancel it out. Or put in any number I want. What do I have to do to get HF by itself? Divide by G. All right, G is gone from that side. G comes over to this side. Am I done? No square root needed here, right? Okay, because H is not squared, so I don't have to put a square root on this. I'm done. I just have to put in my numbers. So that's going to mean 9.81 times 1.2. That height was initial because they left the trampoline and they were moving upwards. So I know that that's the initial height. Plus 1/2 times 1.5 squared. That's how fast they were going at that point. And I divide all of that by 9.81 because there's no speed at the maximum height. All right, so 9.81 times 1.2 plus 0.5 times 1.5 squared. Okay, and divide that by 9.81. All right, so they go from 1.2 to 1.31 meters. They go this much higher. Okay, is that a reasonable answer? It is. If you're only going 1.5 meters per second, gravity is pulling you downwards at 9.81 meters per second squared. At that speed, you're not moving up for very much longer. Okay, it is going to pull you back to Earth in a hurry, as gravity usually does. Okay, so that is absolutely a reasonable number for the maximum height of the person. Okay, and that's another thing that we have to think about. When we get an answer, does this answer make sense? You can. Was that what you're going to ask?
Yeah.
Just both of you go, but don't be gone long. Okay, no parties. All right. Questions on that one? Making sense? Did I still do the same pattern? Okay, always the same pattern. Just make sure, guys, that you are understanding the context of the question. That is where people go wrong on questions like this. You guys can all do that math. That's not the hard part. Okay, the hard part is what's going on here. How do I get to the math? What math do I do? Okay. Okay, try this one. This is a roller coaster. I know my drawing is terrible. Okay, this is a roller coaster, a frictionless one, so it's really cool because it's frictionless. It starts out 200 meters above the ground. This is like the world's scariest roller coaster. At 200 meters above the ground, moving at 4.5 meters per second. A little while later, it is sitting on top of a much smaller hill that is only 50 meters above the ground. How fast is it going there? Okay. Remember that it is a frictionless track. Okay. Give you a few minutes on that one. Are the mechanical energy initial and mechanical energy final equal if I stated that this was a frictionless roller coaster? They are, okay? There's no forces doing any work, changing any energy, okay? So we can establish in this one that our initial mechanical and our final mechanical are equal, okay? So that means initial potential plus initial kinetic equals final potential plus final kinetic. Okay, any of those zero in this question? Nope, none of those are zero. Okay, we're being asked to find the final speed. We're lower than we were at the beginning, but we still have height. So there's initial potential, initial kinetic, final potential, and final kinetic. Okay, so none of those are zero. I can't cancel any of them. I'm looking for VF. Okay, that's part of this term. So how do I isolate kinetic final? Subtract potential final, right? So I'm going to go EP initial plus kinetic initial minus potential final equals kinetic. Okay, now put in my formulas. M times G times H initial plus 1/2 MV initial squared minus MGH final equals 1/2 MV final squared. Okay, M's in every term, so I'm going to cancel it. I just want VF. What do I do with the half? Divide it, yep. Okay, that gets me VF squared. I just want VF, so square root everything. All right, let's get the rest of our numbers in there. So we're going to have 9.81 times 200 plus 1/2 times 4.5 squared. Sorry, they gave us that up here. Okay, that was our initial speed. And then we are subtracting 9.81 times 50, because that was our final height there. And then we are dividing all of that by 1/2. That will give us VF. Okay, so 9.81 times 200 plus 0.5 times 4.5 squared minus 9.81 times 50 divided by 1/2 square root. Okay, 54.4 meters per second. Is that really fast? It is. It's 196 kilometers an hour. This is some kind of really unsafe, wicked roller coaster, okay? No roller coaster is gonna be 200 meters above its lowest point. It would be going way too fast to stay on any corners you could possibly hope to build for it, okay? But in the end, that is a realistic number for what the final speed would be, 50 meters above ground. Imagine how fast it's going here. Okay, it'd be going like it would be going over 200 kilometers an hour. That's really fast. It'd be very exciting if you had no fear of death. Okay, or maybe that's what makes it exciting. I don't know. I'm too old to ride the things anymore. They just make me dizzy and I throw up. Used to be able to ride them like crazy. This happens when you get old. Okay, questions on that one? Does that make sense? Okay, that's about as tricky as they get. Okay, like I usually ask something like that on the unit exam. Okay, but here's the thing, guys. In every one of these questions, you're always asked to find one of two things: height or speed. Okay, the pattern is pretty easy to remember, right? The tricky part, is it a conservation of energy question? What am I looking for, H or V? Okay, do the appropriate manipulation. That's the easy part. Okay, the tricky part is it a conservation of energy question? Are any of the energies zero? Then you go from there, right? Know the pattern, can't really go wrong. How are we feeling about the pattern? Okay, just make sure that's what we know. Okay, then read the question carefully or look at Coderre's terrible diagram carefully, okay, so that you get all the information you need. All right, let's do that one and see where we're at when that one is done. That's probably going to be our last one for the day. Okay, so we have a cannonball fired from ground level at a speed of 425 meters per second. How high above the ground is it when it's moving at 110 meters per second? So cannonballs fired from the ground. So here's ground level. Okay, it's fired at 425 meters per second. That's going to be my what? Initial velocity, or initial speed. Okay, what's my initial height? 0, it says ground level, right? It doesn't have to give me that HI is 0, it told me that. All right, cannonball is going to do what all projectiles do. It's going to follow an arc that encounters the ground some distance away, probably a long distance away, hopefully, preferably a long distance away. Okay, so what I'm looking for here is what height it's at when it's moving at 110 meters per second. Okay, that may or may not be that point. It's somewhere in the arc. Okay, that's what we know. All right, so I'm looking for final height. Is there any mention of friction, air resistance, or anything like that? Okay, then it's not a work energy theorem problem. Okay, plus it gives me heights and speeds, which I can only use with this type of problem. So potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Any of those 0? Which one? Initial potential, says ground level. All right, that's gone. What I'm looking for is HF. HF is part of that term, so I need to isolate that term by doing what to EK final? Subtracting it to the other side. All right, so I'm going to have my initial kinetic energy, which represents my total mechanical energy, okay, minus my final kinetic energy. That will give me my final potential energy. Okay, I'm trying to look for HF, so I got to put that on the board by putting all the formulas in. So 1/2 mvi squared minus 1/2 mvf squared, okay, equals m times g times hf. Okay, m is in every term. Mathematically, it can be eliminated. What do we have to do with g? Divide it over to the other side. Okay, now I'm solving for HF. Put in my numbers. 1/2 times 425 squared minus 1/2 times 110 squared divided by 9.81. Okay, is that a long way up? It is. The thing's moving at 425 meters per second initially. It's going to go a long way up. Okay. Now that may well be the maximum distance up it goes, 8.5 kilometers. That's why you don't want to be underneath the damn thing when it comes back to Earth. Okay, it's heavy. It's going to have a lot of kinetic energy. Plus, we usually lob things that blow up when they hit the ground, so there's that too. Okay, this is exactly how all modern artillery works. We just don't use a ball anymore. Okay, we use something that looks like a giant explosive bullet. Okay, so does that sort of make sense? It is a big number. A lot of people are thrown by that number. They don't like that. They feel like that's too big and they did something wrong, but absolutely not. 425 meters per second is faster than sound. Okay, this cannonball is going to go up a long way. Okay, everybody all right with that? Okay. So going forward here, guys, tomorrow you're going to have a quiz, 2 questions, both conservation of energy questions. Okay, see how that goes. We might take a little more time on conservation of energy stuff before we talk about efficiency. Efficiency is the last thing in the physics unit. We will be done new material tomorrow. Unit exam review on Friday. Unit exam on Monday. Right? You can write into lunch, okay, into scheduled help. I'll give you an extra 20 minutes on the end, okay, of class, because I give my period 1s 20 minutes on the beginning. Okay. If you normally write in learning support, I took your exams there this morning. Okay, they are ready to go for you. And if you have any other accommodations, they're all set up. Okay. If not, show up here. Okay. Usual procedure will apply. You turn off your phone, you put it in the box, they give you your test, you write your test. Okay? What do you need to bring to this test? You need to bring your calculator, charged, fresh batteries, whatever. Okay, make sure that it's got that because you're definitely going to need that. The formulas you need are on the front page of the test. So you don't need your formula sheet, plus I don't know how much you've written on there by now. So, okay, I give you fresh formulas on the front page of the exam. And then a pencil, okay, for at least the multiple choice, but probably also the written response on this test. You're gonna, got a lot of algebra and math and stuff as opposed to writing paragraphs. So I would have that as well. Okay, if you've got, if you're studying, tonight and you got some questions, the only time you can ask me tomorrow, because tomorrow is Friday, is in class while we do the review. That would be the best time. Okay, or before school starts. Okay, get here 5 after 8, and I can answer some questions for you then. But obviously tomorrow we will be reviewing. Alrighty. What's that? Sorry, tomorrow's Thursday. You can ask me tomorrow, and you could ask me Friday morning, and during. You're right. This whole long weekend thing made me think we're further along in the week than we are. Okay, so make sure you're doing some of that. Please do not wait to study until Sunday. Right, that is too late. Right, there's too much stuff for you to practice, and you're not going to be able to lock in for 6 hours effectively. So start doing a little bit each night. Okay, take 15 minutes to a half an hour tonight. Take 15 minutes, half an hour tomorrow. Do a little bit. Chunk it. Okay, put it in little chunks, and then you do a lot more effective studying after. Something else that we're probably going to do after this unit exam is start looking at timeline for finishing up the semester here. Because I want you to kind of look at doing the same thing I just mentioned. That would be managing your time, breaking up the huge tasks that you are going to have, okay, coming towards the end of the semester, and planning when you can work on them little bits at a time, okay, as opposed to having to lock in for hours at a go. Okay, so we'll start looking a little bit at that after the unit exam. Okay, questions from you guys? All right, I will be marking your work labs this afternoon. Okay, hopefully get them back to you before the end of the day. If not, it'll be later on tonight. Okay, and we will go through those tomorrow as well. Okay, all right, that's it for today. Good work, guys.